Imagine a spaceship that could pass right through the Earth without even noticing it was there. A spaceship that could cross the vastness of space at the speed of light and then penetrate into the very heart of subatomic matter to seek out its fundamental structure. Imagine then a particle that is almost nothing, that can tell you almost everything about the structure of matter and the evolution of the universe. This particle exists. It's called Neutrino, and its story begins in 1930.
E la sua storia comincia nel 1930.
As the bearer of these lines, to whom I graciously ask you to listen, I will explain to you in more detail how, because of the wrong statistics of the nitrogen and lithium nuclei and the continuous beta spectrum, I have hit upon a desperate remedy to save the exchange theorem of statistics and the law of conservation of energy. Namely, the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons, which have spin 1/2 and obey the exclusion principle, and which further differ from light quanta in that they do not travel with the velocity of light. I agree that my remedy could seem incredible, because one should have seen those neutrons much earlier if they really exist.
The solution suggested by Pauli in his letter was that the missing energy could be taken away by an unknown particle with a very small mass and no electric charge, thus invisible to instruments.
Che cos'era questo rimedio disperato, assurdo, a cui allude il grande fisico Wolfgang Pauli nella sua
lettera? What was this absurd, desperate remedy Pauli is hinting at in his letter to the radioactive friends? What was the enigma that puzzled the greatest minds of the early 1900s? The mystery had to do with radioactivity.
At the end of the 1800s, French scientists Marie and Pierre Curie and Henri Becquerel discovered a strange phenomenon in some minerals containing uranium and radium. These elements emitted radiation that left its mark on photographic films. They had discovered radioactivity, a property of some nuclei that, because of an excess number of protons and neutrons, mutate into different nuclei, emitting particles in the process. There are three kinds of radioactive decay: alpha, beta and gamma, according to the subatomic fragments emitted. During alpha decay, an atom's nucleus sheds 2 protons and 2 neutrons in a packet that scientists call an alpha particle. In this case, the particle emitted leaves the nucleus by penetrating a potential barrier. During beta decay, a neutron from the nucleus turns into a proton and emits an electron and a neutrino. But the only observed particle is an electron. If the electron were the only particle emitted, its energy would always have the same value. Instead, to their great surprise, physicists obtained a different energy value for the electron each time. Radioactivity was a real puzzle for physicists, as it seemed to violate the sacred principle of energy conservation. In the beta radioactive decay, the final energy was not conserved. Something was missing.
Mysteriously, their energy missing, momentum missing. So it was first suggested by Pauli, but not published, because Pauli also was very much afraid to. Pauli was a great theorist, but very conservative. So he thought there could be a particle So consequently, he made suggestions, but not written down.
The mass of neutrons should be of the same order of magnitude as the electron mass, and in any event not larger than 0.01 proton masses. The continuous beta spectrum would then become understandable by the assumption that in beta decay a neutron is emitted in addition to the electron, such that the sum of the energies of the neutron and the electron is constant.
The solution suggested by Pauli in his letter was the existence of an unknown particle with a very small mass and zero electric charge that he called neutron. At the time, the particles which we call neutron, and which form the atomic nucleus with protons, had not been discovered.
I agree that my remedy could seem incredible, because one should have seen those neutrons much earlier if they really exist. But only the one who dare can win. Unfortunately, I cannot appear in Tübingen personally, since I am indispensable here in Zurich because of a ball. With my best regards to you, also to Mr. Beck. Your humble servant, Wolfgang Pauli, December 1930.
A few years later, in 1934, Italian physicist Enrico Fermi christened the particle neutrino, and the name stuck. Fermi also developed a theory that included and explained the role of this particle in fundamental physics, the theory of weak interactions.
Suggestions which is quite unclear how it can be incorporated into the theory. And it was Professor Enrico Fermi who not only incorporated the concrete idea and wrote down the concrete interaction and the theory, and that was the famous Fermi's theory of beta decay. And this is how neutrino was introduced.
We are now in the historical library of the Scuola Normale. At Fermi's time, this was also the students' library. Fermi was here from 1918 to 1922, and especially as a student, he worked on general relativity and quantum mechanics.
Era ormai abbastanza chiaro che il processo che dava luogo.
In 1933, it was pretty clear that neutrinos were generated by the beta decay process. In this process, a neutron from the nucleus turned into a proton and emitted an electron plus a particle called neutrino, that was the one necessary to conserve the energy. Fermi's theory was inspired by a comparison with the electromagnetic process. An excited atom, let's call it star, emits electromagnetic radiation that we call gamma. In this process, the photon, or gamma, that is the electromagnetic radiation, is created by the disexcitation of the excited atom. Inspired by this theory, Fermi concluded that also the couple electron-neutrino is created by a new interaction, different from the one that creates electromagnetic light, and this new interaction is the one causing neutron decay. Its name is weak interaction. Fermi built a simple theory of it, based on a constant, G, now called Fermi's constant, one of the fundamental constants of nature.
Fermi's theory convinced all physicists that neutrinos had to exist, but it had to be demonstrated experimentally. The hunt for neutrinos started everywhere in the world, with a large deployment of resources to prove its existence. In 1951, when American physicists Fred Raines and Clyde Cowan started thinking about a large experiment to capture neutrinos, this particle was still an elusive ghost haunting the world of physical reality, a real poltergeist. Raines and Cowan had taken part in the Manhattan Project and had stayed at Los Alamos Laboratories in New Mexico. After the war, they were looking for a fundamental physics problem to solve, using all their knowledge from the development of the American bomb. Together, they had the idea of proving the existence of neutrinos using a powerful nuclear explosion.
Rhines e Cowan hanno individuato la risposta giusta per poter fare questo esperimento.
Rhines and Cowan found the right way to perform this experiment. The problem is that neutrinos interact very little, and their experiment got through this by simply increasing the mass of the detector and the intensity of the neutrino source. A reactor that works by nuclear fission emits something like 10 to the 21st neutrinos per second, a huge quantity. An atom bomb emits an even more incredible quantity of neutrinos.
La proposta che venne fuori dopo è quella.
Initially, Rhines and Cowan, supported by Fermi, planned using a nuclear bomb to detect neutrinos, but then considered using a nuclear reactor and told Fermi. Fermi said this was a good idea, because with a reactor the experiment could be repeated.
The method Rhines and Cowan finally used to detect neutrinos was based on the interaction of an antineutrino emitted by the fission reaction with one of the billions of protons contained in the large mass of water in the apparatus. A proton in the water would first absorb one of the antineutrinos and produce a neutron and a positron. Then, almost immediately, the positron would annihilate with an electron, emitting 2 gamma rays. Unlike neutrinos, gamma rays are sensitive to the electromagnetic force and can be detected by the instruments, layers and layers of scintillators which line the apparatus. What about the neutron? Some 5 microseconds after the annihilation gamma rays had emerged, the neutron would be captured by a cadmium nucleus also contained in the water, which would then emit some more gamma rays.
New technologies were developed for this experiment, such as liquid scintillators. For the first time, we have an experiment that was really big, so big, as Rhines himself said during an interview, that a person could go inside it. This was of an unprecedented scale.
On the 14th of June 1956, Rhines and Cowan sent a telegram to Pauli to tell him of their success. We are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. For this discovery, they were awarded the Nobel Prize for Physics in 1995. The neutrino Rhines and Cowan found was the electron neutrino, the first of 3 different families.
There would be, at the time of Fermi and the time of Cowan-Rhines, people did not suspect there would be the second one. This is because its origin came from the muon in cosmic radiation. And from the muon, first it was a theoretical hypothesis, which muon does not decay to electron. And then both CERN and Brookhaven made search for it. And Brookhaven was a little bit ahead of CERN. So that was discovered by Steinberger, who's now at CERN, and Lederman and Schwartz.
It's true that we had the chance to do a first experiment with neutrinos. It's not quite true, but let's leave it like that. At least with accelerated produced neutrinos. But it was maybe not because we were particularly clever. I think it's because the time was the right time for it. The neutrinos are produced, first of all you have to produce some high energy particle, which were protons, and these were allowed to strike some target, doesn't matter very much what target, and produced are then pi mesons, and these pi mesons decay in a short distance with one of the particles that comes out as a neutrino. And so this made a beam of neutrinos, and then we had to make a detector. It was a bit new kind of detector which we had to build, but not particularly difficult, using techniques which were more or less known. And we were, for the first time in this way, able to see something like 30 events produced by these neutrinos after a few months of operation. And these showed that this neutrino, which is produced in the decay of the pi meson, is not the same as a neutrino which is produced in beta decay, in radioactive decay of nuclei. So we had found a different kind of neutrino.
Three families is even more interesting, and this was then later made a slab. And that then the three seem to be, at this moment, seem to complete the three families. Not only three families of leptons, and three families of quarks. And this is what we regard that altogether there are only six these fundamental particles. Neutrinos are three, they are neutral. They are not quiescent, they oscillate.
The idea that a neutrino could oscillate from one type to another, and that the different types of neutrinos were nothing but different states of the same particle, is due to Italian physicist Bruno Pontecorvo. Pontecorvo noted that the rigid classification of neutrinos in three different families would be true only if the neutrino's mass was zero. If the neutrino had a mass, it could be a mixing of the three families, electronic, muonic and tauonic. In this case, it would be possible to see the neutrinos oscillate, that is, turn into the next family as a function of time.
Adesso noi sappiamo che ci sono tre famiglie di neutrini.
We know today that there are three families of neutrinos, as was proved by the experiment at the LEP accelerator, Large Electron Positron Collider, here at CERN in Geneva. This experiment has shown that there are only three families of neutrino: electronic, muonic and tauonic, the latter being just a heavier version of the electron. LEP has now been dismantled to make room for a more powerful accelerator called the LHC, Large Hadron Collider. We are now in the LHC tunnel, in the cavern hosting the largest LHC experiment. You can see it behind me. It's called Atlas. These experiments see neutrinos only indirectly, and what they actually see is a huge lack of energy, because the neutrino does not interact. It takes away a large chunk of the interaction energy. Bruno Pontecorvo is mainly remembered as the first to propose the theory of neutrino oscillations. According to this theory, a neutrino during its life can change family. An electron neutrino can turn into a mu neutrino, for instance. I am very sorry Bruno has not lived enough to see his theory confirmed by the superchemical experiment. Answering the question if he was angry because he never got the Nobel Prize, he said, "Receiving a prize is always pleasant, but the experimental proof of a theory one has proposed or performing a wonderful experiment can generate such joy that no prize can give you."
At CERN in Geneva, the largest physics lab in the world, they've just built a special scientific instrument to study neutrinos. It's called CNGS, CERN Neutrinos to Gran Sasso, and it's a beam of neutrinos starting off right under my feet, directed to the Gran Sasso Labs in central Italy.
Qui ci troviamo in un tunnel connesso con l'acceleratore da 400 miliardi di electronvolt del CERN a Ginevra.
And right here are generated the neutrinos that the Italian laboratory of Gran Sasso will use to study the oscillations between the second and third family. Since the accelerator is built on a horizontal plane, the first thing to do is to deflect the protons traveling inside these red objects. These are electromagnets used to deflect protons in the direction of Gran Sasso. Because the Earth is round, they must be deflected in the vertical plane as well. These protons will so travel inside these deflecting magnets behind me, and after a while they will hit the target, a graphite cylinder with which they interact. During these interactions, the protons produce mesons, which are relatively light and unstable particles, charged positively or negatively. When these mesons decay, they produce neutrinos. We are interested only in the neutrinos produced by the positively charged mesons. So behind the target, we have two magnetic lenses, called horn and reflector, that squeeze the positive mesons in a parallel beam. This beam is then sent inside a 1 kilometer long vacuum tunnel, called the decay tunnel, where the mesons decay and produce the neutrinos we need. The neutrinos then cross the Earth and re-emerge at Gran Sasso, where they find detectors capable of measuring the neutrino oscillations. In 1998, atmospheric neutrinos were discovered, and this discovery provided important indications on the mass difference between the neutrinos of the second and third family. The conclusion was that the optimum distance to measure the oscillations of the second family neutrino into the third one is of the order of 1,500 kilometers. The distance between CERN and Gran Sasso is 730 kilometers, which is enough to study the oscillations because their amplitude is big enough to generate a large number of third family neutrinos during the voyage from CERN to Gran Sasso.
And this is where the neutrino beam from CERN gets to, right here in the heart of the Gran Sasso National Laboratories, the largest in the world for underground physics. This is the underground area of the Gran Sasso Laboratories hosting the OPERA experiment, and Yves Decay is the spokesperson of the international collaboration that runs this very large detector. Yves, how will OPERA see neutrinos and their passage?
I will now show you how the detector will register the neutrino interactions in the lead it is made of, and how we will later analyze events to identify the nature of the neutrino that interacted. On this very light mechanical structure, we will install special bricks made of 50 sheets of lead and 50 sheets of emulsion, a special substance similar to photographic film that can record in a very precise way the passage of the particles coming from the interaction of a neutrino with a brick. We have 30 tons of bricks and a total of 12 million sheets of emulsion to record the interaction. The whole point will be to determine in which brick the interaction took place, and to do this, we put layers of detectors called scintillators in between each layer of brick. These scintillators record the passage of particles in real time. Knowing the time correspondence between the passage of particles and the time of departure of the beam from CERN, we can make the difference between the interaction generated by the beam and the interaction from the background noise due to cosmic rays, that are anyway very weak in this underground camera. The difficulty of this experiment will be to determine which interaction is the one identifying the tau neutrino. Here is one of the 200,000 elements of the OPERA target, one of the 200,000 bricks that will be put inside the detector by a robot. Each of them weighs 8 kilograms, so the total weight of the bricks inside OPERA will be 1,800 tons.
and I am honored to place the first of the 206,000 bricks of opera. This laboratory had just been created when in 1987 a supernova exploded and brought the Nobel Prize for Physics to the Japanese scientist who could see some of its neutrinos, Masatoshi Koshiba.
Well, that was a very, very lucky thing. This supernova, which occurred in the southern sky, traveled 170,000 years to arrive at the Earth, and then enter the Earth near Borneo Island and came to the direction of Japan through the inside of Earth, and then reached our detector, okay? And then they left 11 events. Yeah. And even though the number is small, those 11 events told us very good things about supernova explosion, okay? Observe this positive. The probability of making this collision is much higher than making a collision with electron.
An important result in the study of solar neutrinos was obtained in this laboratory with the GALLEX experiment. Let's hear about it from the director of the Gran Sasso Laboratory, Professor Eugenio Coccia.
Allora, questo esperimento così importante.
GALLEX
has so far obtained the most important result at the Gran Sasso Laboratories. We found out that the flow of neutrinos from the Sun was half the expected number. This mystery had remained unsolved for a number of years, since the time of Davis. It was solved by putting together data from various experiments, and the role of GALLEX was fundamental because it found a solution in the neutrino oscillations. Some of the electron-neutrinos expected to come from the Sun are missing because they turn into muon neutrinos during their voyage. This transformation is of paramount importance for the laws of physics, regulating particle interactions, because if the neutrino changes in time, this means it does not travel at the speed of light, and it has a mass. This is very important in particle physics, but also in cosmology.
Now that GALLEX is concluded, how does solar physics continue here at Gran Sasso?
Another important experiment following in the path of GALLEX is Borexino.
Dunque, noi siamo qui nella parte esterna del rivelatore Borexino. La parte interna è dentro questo.
We are now inside the Borexino detector. The core of the detector is inside this sphere, supporting almost 1,500 electronic eyes that capture photons generated by the interaction of neutrinos with a scintillating liquid inside a nylon balloon. The purpose of the external layer of the detector is twofold. First, to create a shield against external radioactivity, because Borexino must have a very low radioactivity. This is the only experiment that can measure low-energy solar neutrinos, and we must keep radioactivity low. The second purpose is to detect the residual cosmic rays making their way through the rock and through the water of the detector. When these pass through the water, they generate light, and we detect it with these electronic eyes called phototubes, which capture these photons from the water. Since the emission of light in the water is very low, we added these white Kevlar sheets to diffuse the light produced by cosmic rays as much as possible.
maggiore possibile la luce prodotta da questi raggi cosmici. Lo studio dei neutrini solari è importante, come forse è già stato detto.
The study of solar neutrinos is important, not just to understand oscillations, but also to study the Sun, because neutrinos are the only particles that escape the matter density inside the Sun.
Materia che c'è nel Sole, e quindi a dare delle notizie su cosa avviene all'interno del Sole.
Esistono neutrini da varie sorgenti.
Neutrinos come from different sources, and we try to analyze and understand them. Neutrinos are emitted by collapsing stars or by the Sun, and these are astrophysical or cosmic neutrinos. Some are originating in the atmosphere by the impact of primary particles, essentially protons, with layers of the atmosphere itself. Finally, neutrinos can also be originated by radioactivity inside the Earth. Of course, in the next few years, attention is going to be focused on artificially made neutrinos. The neutrino beam from CERN is a titanic enterprise. I would like to underline that also reactions supposed to emit neutrinos that we don't find can say a lot on the neutrino's nature.
Paradossalmente anche reazioni in cui i neutrini dovrebbero essere emessi ma non si vedono possono dire moltissimo sul neutrino stesso.
A still unsolved mystery is whether the neutrino is the same as its antineutrino or not. According to Paul Dirac, neutrino and antineutrino are two different particles. The solution is to be found in the study of a very rare radioactive phenomenon called double beta decay, that is the emission of two and not just one electron. If neutrinos and antineutrinos are different, two electrons and two neutrinos will be emitted, and the energy distribution of the two electrons will be different each time, continuous. According to Ettore Majorana, neutrino and antineutrino are the same particle, and the distribution of the energy of the two electrons will always be the same, a fixed value. But the solution is waiting for experiments to catch a double beta decay. The hunt for neutrinos has not stopped, and the resources deployed worldwide are incredible. Giant sophisticated instruments are being placed in the most remote spots on the planet. Beneath mountains, on the bottom of huge pools, or inside the tunnels of disused mines, deep under the sea, and even beneath the ice of Antarctica.
NEMO è un progetto dell'Istituto Nazionale di Fisica Nucleare e mira alla rivelazione.
NEMO is an experiment funded by INFN, the Italian Institute for Nuclear Physics, and its purpose is to detect neutrinos coming from the cosmos that we call astrophysics neutrinos. It is important to detect these particles because they come from intergalactic space over long distances, without being transformed or absorbed by anything they find on their path. For this reason, these cosmic neutrinos carry information from the deepest and densest corners of the cosmos, such as the regions close to the black holes. We can use them to start what we call neutrino astrophysics, a new way of studying the cosmos. But to do this, we need detectors of a magnitude of the cubic kilometers, equipped with several thousand optical sensors, from 5 to 6,000. And where would you place such huge machines? A good place is below the Antarctic ice sheet, another the bottom of the sea. In addition, if we want a complete observation of the celestial vault, we need two such telescopes, one in the northern hemisphere, another one in the southern. 3 collaborations are active around the neutrino telescope in the Mediterranean Sea, in France, in Greece and in Italy with our experiment NEMO. The NEMO collaboration is now busy on 2 main activities. First, identify a good site to place the telescope, and this activity is now concluded. as we just found an ideal site 3,500 meters deep under sea, 100 kilometers off the coast southeast of Capo Passaro in Sicily. Our other activity just started is advanced R&D, to find all the technological solutions to make the telescope work and carry out such a difficult and complex research activity. This is frontier technology. So far, we've completed the design of the detector and started building some prototypes and modules of the structure, and we are testing their reliability and operation.
Ci sono varie linee sperimentali sui neutrini. Alcune tendono a
Many different experiments are being carried out on neutrinos. Some try to understand its basic feature, like the Gran Sasso experiment that is studying and testing the oscillation from a mu neutrino into a tau neutrino. Other experiments use the low interactivity of neutrinos to bring us a picture of the far universe, because these neutrinos cross galaxies, planets, stars, and can provide information on the time when the universe was born, because looking far in the universe means looking back in time.
Informazioni del momento in cui l'universo era appena nato, perché guardare lontano l'universo vuol dire guardare all'indietro nel tempo.
But while cosmologists and particle physicists prepare for battle with new telescopes and huge detectors in deep caverns, beneath seas and even Antarctic ice, somebody is wondering if neutrinos may one day be of any practical use.
Now, you know, many people ask me the question, what's the good of studying neutrinos? What profit can we expect? I always say there's no profit at all, okay? But there are things you can do with neutrinos in the future. For instance, I talked about anti-neutrino, okay? Those anti-neutrinos are emitted from the radioactive nuclei like uranium or thorium, okay? They are deep inside the earth. Nobody knows where how many tons of uranium or thorium exist. But if you do distribute our universe after 3 seconds after its birth, this is really something. Only 3 seconds after its birth. They are fantastic possibility.
Proposed in the late 30s to explain beta radioactive decay, the most elusive of all particles, he is hiding the most intimate secrets of the structure of the universe and the subatomic world. Disclosing the absolute value of the neutrino's mass will clarify its role in the formation of the large structures of the cosmos. This mysterious messenger of nature, coming unchanged from the depths of the cosmos, still carries with it the primordial footprints of the creation of the universe. And it has not stopped surprising us.